Hello, Gen Bio. Welcome to our lab on enzyme kinetics, which in your lab manual is listed as lab 5, but I believe is actually lab 6. So this week we are going to be looking at enzymatic reactions and how they proceed, and we're going to actually be able to watch them in real time during the course of the lab today. So we're going to move to our first slide here. The goal of this week's lab is to demonstrate the effect that we can create of altering our substrate and our enzyme concentrations on the speed, the rate that an enzymatic reaction takes place. Okay, so the enzyme that we're using is called polyphenol oxidase. And we are able to use this because it is relatively stable and extracted readily from potato tubers. So the tuber is the part of the potato that we eat, and it can be easily extracted and used for our lab this week. And it catalyzes the reaction, the oxidation of catechol and molecular oxygen. These are our reactants, our substrates, into cis-muconic acid and water. Those are our two products, okay? So we're gonna flip to the next slide where I have this reaction mapped out again for you. So molecular oxygen and catechol are what goes in. These are the substrates or reactants. And then the products are cis-muconic acid and water, okay? So that's basically the mapping out of our enzymatic reaction. And of course, the reaction itself is catalyzed by our enzyme, polyphenol oxidase. So it helps to facilitate this reaction. Now, something I will point out, and I want you to keep in mind as we go along, is that catechols, our product, or excuse me, our reactant, these are colorless, okay? But the product, cis-muconic acid, has a yellowish brown tint to it. So you're actually familiar with this reaction already, although you may not know it. You've probably observed this many times. When you leave apples or potatoes out and they're exposed to the air, so when they're exposed to oxygen, then you've seen that they take on a brownish pigment to them. They turn brown when they're left out in the air, right? This is because this is actually a protective measure for the plant, because when the plant cells are broken open and exposed to the oxygen, then polyphenol oxidase catalyzes the reaction that causes that wounded surface, the broken cells, to secrete this brown coating. It's a substance that's actually an antibacterial, antifungal product for the plant. So it's actually a protective measure for the plant, but it's not so appetizing. So a lot of times people try to stop the reaction, either if they're providing food, so like food scientists or restaurants, or even like if you ever took apples in your lunch and your mom cut up the apples for you, she might douse them in lemon juice, because this is one way of a few that we're going to talk about that you can stop or slow down this reaction taking place. So let's talk about those a little bit. The different ways that the reaction can be halted include blanching, which is a quick dip in boiling water, okay? Covering with water, so just submerging the apple or the potato in water. You don't have to boil it. That should also do the trick. Coating with vinegar or lemon juice would also slow or stop the reaction. And these different methods work in different ways, and you should be able to think about why these would halt the reaction. So for blanching, really quick dip in boiling water, you might recognize that as the environment is heated so much so that you can actually denature proteins, then you're probably going to denature your enzyme, which is going to make it lose its structure and therefore be unable to catalyze the reaction. So that's what happens when you dip them in boiling water. you're actually denaturing the enzyme, and so therefore the reaction isn't going to take place very readily. Okay, covering in water, this one prohibits access of one of our reactants, one of our substrates. If you look at our equation here, our reaction, one of the ingredients that has to go in is a molecular oxygen, which does not pass very readily through water. And so if you cover the potatoes or the apples in water, then you're prohibiting access of oxygen to that reaction. So it won't be able to be a substrate, and therefore the reaction won't proceed. Okay. And the last one I hinted at already, a lot of times you might coat your apple slices in lemon juice to prohibit them from browning, because this then changes the acidity of the environment. And so this would also cause a change in the enzyme. It might denature it such that it wouldn't be able to bind and enable the reaction to take place at the same rate as it would had the pH been at a very stable or beneficial state for the reaction to proceed. Okay, so let's flip to the next slide. The goal of our experiment today is to watch the reaction take place. We're going to watch it happen in real time. We're going to manipulate the conditions a little bit so we can see it happening under different concentrations of our substrate, and then also separately under different concentrations of our enzyme, and be able to watch the change in the reaction and see which of these conditions enables the reaction to take place at the quickest, at the speediest rate. So the thing that I wanted to keep in mind from our last slide, which is coming up again here, is that this reaction can be monitored relatively easily because of the characteristic of the product being a different color from the substrate. So our cis-muconic acid, the product, is a brownish color, right? We already know how to quantify color change, right? We've done this several times in the lab. So in order to quantify color change, we're going to use the spectrophotometer and observe how much light is absorbed by the solution that, as the reaction proceeds, should be getting darker, right? As this reaction takes place, there should be more and more product formed. And as that happens, you should be seeing more of that brown color. And we can quantify this then by monitoring how much light is absorbed. So we're going to use a wavelength of 430 nanometers as the wavelength that we're going to monitor absorption of cis-muconic acid. So as the solution gets darker, then it should absorb more light, and we can then observe that and graph it and be able to see the reaction happening then. So we're going to plot the absorbance in real time, making one absorbance reading per second. And so as this absorbance as the absorbance value should increase over time, then we can basically observe the reaction happening, okay? So let's flip to our next slide to see what that would look like. So the graph shown here is what we call a time course, which just means that we're looking at the reaction over time, okay? So on our x-axis, you can see that time is in seconds. And then on our y-axis, this is the amount of product formed as measured by our absorbance value. Okay, so as the reaction proceeds, you will get an absorbance reading every second. And so you will get values that then will look something like this graph here. So where you see an increase, a more drastic increase in the reaction rate towards the beginning, and then it tends to level off as time goes on, okay? So what we want to look at then when we have this time course is the initial rate, the rate at the start of the reaction when it's occurring most rapidly. And to measure this, we use the concept of rise over run. So change in y, change in our y-axis, so change in the amount of the product formed over the change in time, which is on our x-axis. So change in y over change in x, okay? Rise over run, okay? And you can hand calculate this by just picking 2 points in this initial rate zone. You can pick, so right here, this point and the previous one, where you could say, okay, well, my change in y is going to be 100 minus 50. So the change is going to be 50. So 100 minus 50, change is going to be 50 in absorbance units. And then that goes over the change in x, so the change in time. So at this point, it looks like about 10 seconds. And at the previous point, it looks like maybe about 5 seconds. So you would put that on the bottom half of our equation. 10 minus 5 is equal to 5. So then when you do calculate it out, you get 10 absorbance units per second, okay? And that is our initial rate, okay? Now, you can obviously hand do this, or there's a special button on the computer, which I'll show you in lab. So you can just use the slope button and draw the tangent line at the beginning of the graph, and that will calculate it for you, and you can record that. So it's a little shortcut, but just so you know how to actually calculate by hand if you have to. All right, so let's move to our next slide. We want to look at different variables that will affect the product formation. And the 2 that we're going to focus on are substrate concentration and enzyme concentration. Others would include pH and temperature. These should all affect the rate of product formation in an enzymatic reaction, but we're going to focus on the first 2. And we're going to do different time courses for several different enzyme concentrations, as well as separately several different substrate concentrations. So we're going to do each of those different concentrations of enzyme 2 to 3 times and take the average. And then we're going to do each of the several different substrate concentrations 2 to 3 times, take the average, okay? The average initial rate is what we want then for each of those conditions. And we're going to use that to create graphs. And then what we can see is the optimal conditions for the experiment, for the reaction to take place. So I'm going to give you an example on our next slide here using pH, but you in lab will do enzyme and substrate concentrations. So once you've done your time courses, you're going to take the initial rates from each of your, again, you're doing like 2 to 3 time courses per condition. So for each enzyme concentration, you're going to do that 2 to 3 times. For each substrate concentration, you're going to do that 2 to 3 times. And graph, you're going to average your initial rates and graph those. So each of the data points here is the average initial rate. So here is the average initial rate for a pH of what appears to be about 6.5 for this one. This one would be the average initial rate for a pH of 7, okay, just for example. You will do this also, you're gonna plot the average initial rate but for substrate concentration in a separate graph showing the average initial rates for each of the different enzyme concentrations, okay? So this then, if we were looking at pH, we would see then that there's an optimal pH at which the reaction is able to proceed, and so that would help us to fine-tune how we want our experiments to go in the future. Okay, so this is just an example. Looking at the other variables, so this is our pH graph. Temperature, what you would expect is that with an increase in temperature, you would see an increase in the reaction rate, the initial rate, until you get to a certain point where you will see that the rate dramatically drops. And this is due, as I mentioned previously, to the fact that there's going to be denaturing of the enzyme at too high of a temperature for the enzyme to maintain its structure. So at that point then, you're going to see a sudden drop in the enzymatic rate because of the enzyme denaturing, okay? The bottom 2 pictures here on this slide should, after your experiments, look a lot like your 2 graphs that you will be making, where you see that as you increase enzyme concentration, so here on the x-axis, as you increase enzyme concentration, your reaction rate should increase pretty linearly. Now, if you look at the substrate concentration, it looks a little bit different. As you increase substrate concentration, you will get an initial increase in the reaction rate, but it will level off into what we call Vmax, okay? This is because in physiologic conditions, the enzyme is our rate limiting factor. So at some point, even if you add more substrate, there's not enough enzyme for the reaction to continue to increase. Then you will see this tapering off, this leveling off, because all the enzyme is already being met by substrate. So even if you pour more substrate in there, you can't increase the rate any further because all of that enzyme is already saturated, okay? All right, so those two are similar to what you will be creating after this week's lab. All right, so let's go to our last slide. This is just practical information about what you'll be doing this week. First thing you're going to do is prepare your substrate, which is catechol. You're going to be given it, it's going to be in granular form, and you're going to mix it with buffer in order to create that in a liquid solution. And then the enzyme will be given to you. It should be prepared prior to your arrival. You want to keep both of those on ice, again, so that we don't have any denaturation. And then just try to keep in mind that you want to be speedy, okay? The reaction happens quickly. It happens very quickly. So one tip is you have to mix the substrate and the enzyme. One tip is to cut parafilm pieces prior to mixing them, so that then when you pipette your enzyme into your substrate, you can use a piece of parafilm, invert it a couple times quickly, and stick it right in the spectrophotometer, okay? You want to be as quick as possible while still, getting it mixed, so that you don't miss the initial rate. If you're too slow, it's already going to taper off by the time you get it in there. So it might take a couple times of practice before you get the hang of it, but that's okay, okay? You want to try to get as quick as you can with that so you catch the initial rate, okay? All right. So then from your time courses, which again, you're going to do a couple times an average, you want to acquire the initial rate by using that slope button, okay? And then you're going to make different dilutions. You're going to make different dilutions of enzymes. So you have different concentrations of enzyme. And then you're going to make different dilutions of substrate. And you're going to have different concentrations of those. And combine those, run time courses for each. And one other thing I want to point out, one other thing I want to point out, which is also in your lab manual, when you get to the different dilutions of substrate, you have to recalibrate, okay, every single time, because that's your starting material. You want to reblanket to the new concentration of substrate, okay? And then once you have all your time courses and you've got your initial rates, you're going to make two graphs, one for the various enzyme concentrations, one for the various substrate concentrations. And you're going to make those graphs so that we can see the average initial rate for each of those different concentrations, okay? And they should look similar to the two graphs here that I showed you here. Enzyme, which is going to be hopefully more linear, and then the substrate concentrations which will taper off because of the limited amount of enzyme present, okay? All right, so that wraps up our video. Any questions, you can always shoot me an email, cfry@lvc.edu, and I will see you soon. Have a good week.